Introduction. Two related phenomena have emerged in recent decades: the quickening pace of industrialization and the rise in Earth's surface temperature brought on by an increase in greenhouse gas concentrations in the atmosphere. Because of this, the scientific community is inspired to find methods to lower overall emissions by switching from conventional energy sources to renewable ones, like the sun. Solar cell devices based on perovskite materials have proven to be promising alternatives to silicon-based materials in recent decades. In just a few years, they reached an efficiency of 26.1%. In this family, cesium lead iodide is one of the most interesting photoactive materials, and its band gap of 1.75 eV makes it suitable for tandem devices. It is currently difficult to achieve sufficiently extended stability with this material. However, with the use of europium as a dopant, it is possible to stabilize the photoactive phase. The function of the photoactive layer in a solar cell structure is the transformation of incoming photons into electron-hole pairs, and corresponding transport layers must be included in the architecture to prevent their recombination. In this case, titanium dioxide, which has a multi-branched structure, called Gig-Lox, was used as the ETL. Because of the blending of the two materials, the deposition and infiltration of perovskite into a mesoporous substrate may cause a local structural rearrangement of the perovskite crystals and a modification of the electronic properties, which may have an impact on device performance. This study indeed focuses on a deep characterization of europium-doped cesium lead iodide lattice parameters after infiltration into a thick layer of Gig-Lox titanium dioxide. The structure was investigated using a diffractometer, and 3 different analyses were performed: X-ray reflectivity and X-ray diffraction using the grazing angle and symmetric 2 theta or omega configurations. All the results were compared with a reference layer of perovskite deposited on glass. X-ray reflectivity. Using the XRR technique, we measured the density of the layer surface. The 2 samples present a critical angle for total external reflection equal to 0.285 degree. This means that they have the same electron density at the sample surface. Thus, we argue that the blended material has a cap layer of pure perovskite with a density of 4.707 grams per cubic meter. X-ray diffraction. But how thick is the cap layer? Using the XRD grazing angle configuration and the calculated density, we evaluated the penetration depths according to the different incidence angles. Since, at a certain point, the X-rays will also reach the blend structure, we calculated another penetration depth considering its density. By comparing the calculated penetration depth and the grazing angle patterns, we observed the characteristic peak of the Gig-Lox titanium dioxide at between 0.4 and 0.6 degrees. Thus, we argue that the thickness of the cap layer is between 40 and 70 nanometers. After the crystal analysis of the cap layer, we investigated the internal part of the blended structure using the symmetrical XRD2 theta or omega configuration. We observed several differences between the blended material and the reference. First, there is a shift in the perovskite's peak positions, which indicates different lattice parameters. In addition, we used the peaks FWHM to calculate the sizes of crystallites, and we found a smaller average size of crystallites inside the blended material compared with the reference. This is probably due to the structural confinement, which promotes the formation of smaller crystallites inside the Gig-Lox titanium dioxide. Spectroscopic ellipsometry. To complement the study, we measured the absorption coefficient of the blended structure with ellipsometry measurements. We observed that despite the different lattice parameters, the absorption spectra of perovskite films are similar in terms of band gap energy and absorption peaks at higher energies. Photoluminescence spectroscopy. To explore the applicability of the blended material to solar cell devices, we performed photoluminescence measurements to understand the role played by titanium dioxide in charge extraction. According to the results, the blended material exhibits a drastically lower intensity compared with the reference and, in both cases, the peak is centered at 710 nanometers, corresponding to a band gap of 1.75 eV. These findings address the occurrence of an effective charge carrier injection from the infiltrated perovskite into the Gig-Lox titanium dioxide. Conclusion. Using XRR and grazing angle XRD, we observed a cap layer of pure perovskite on the top of the blended structure, with a thickness between 40 and 70 nanometers. Using the 2θ or omega XRD configuration, we saw that the perovskite crystals infiltrated into the spongy titanium dioxide show a systematic lattice relaxation. We measured the absorption and the emission spectra, and despite the change in the crystal structure, no optical structures were observed. In addition, we found strong quenching of the photoluminescence intensity, which signals the effective injection of photo-generated carriers from the perovskite into the titanium dioxide through the many established interfaces. Do you want to show your research progress to more scholars? Contribute an entry that will be linked to your paper on the EuCl3 platform, providing an opportunity for over 35,000 scholars to access and explore your research. Have you ever tried to show your latest research in a vivid way? EuCl3 Player provides video production services to scholars. The service is in the trial phase and is currently free of charge. We welcome scholars interested in collaboration. Leave your information and we will contact you. Do you want to publish a new paper? EuCl3 has an international, peer-reviewed, and open-access journal. Do you require a discount when you publish research in journals? Anyone who contributes to EuCl3 can obtain vouchers for MDPI Journal's article processing charges. EuCl3 aims to create an open-access knowledge-sharing platform for all scholars. To find more information, search for encyclopedia.pub.